We're going to see now the last rule for differentiation of the last rule of differentiation of for functions, and this could be called the rule for the derivative of the inverse function. So first of all, let's recall a few things about the inverse function. So if we have a function f from a set A to a set B that is one-to-one and onto, and let's explain these two terms. So by one-to-one, if we would like to draw a Venn diagram, then one-to-one means that different inputs go to different outputs. And the term onto means that every element of the second set is an output. So every element of B is an output. Then if somebody gives you an element of B, you have a clear way of how to go back. For the first picture, let me just say that an one-to-one function doesn't have to be onto, so you could have this kind of situation here. So this particular point, this particular element is not the output of anything from the set A. And the second function, the red one that I drew, you can see that it's not one-to-one, but it's onto. But suppose now that you have a function that satisfies both, right? So you have a situation like this. A really nice variety. And the point is that if you start with an element on the second set, then you have a clear way of going back and knowing what it came from. And you can do this for all elements. And this new function that you define this way is called the inverse function, and it goes from B to A. Now, in our case, maybe the nicest example is the example of the exponential function. So the exponential function is a function that goes from R to just a set of positive numbers. We never get a negative number this way, with f of x is equal to e to the x. So now, if somebody wants us to go back, meaning they want us to have a number y and ask e to what number is equal to y and answer that question, then we know that the answer to that question is the logarithm of y. So we have f from the positive numbers. That's exactly where the logarithm is defined, or the natural logarithm for that matter. And maybe I should not, I should say f to the negative 1, actually. From the positive numbers to r, with f to the negative 1 of x is equal to ln of x. And basically what happens, which is true for any pair of functions of a function and its inverse, is that if you feed the inverse into the function, you just come back to any specific number, you just get the identity function. In elementary mathematics, sometimes they call this, actually we're doing elementary mathematics, they call this the round trip formulas or the round trip theorem. And in the case of the exponential function, this simply reads that e to the ln of x is x, and ln of e to the x is x. Okay, which are pretty much the formulas that can be considered to define the logarithmic function. So with all of that in mind, we can ask the following simple question. What is the derivative of the inverse of a function? And here we have a kind of interesting picture that we could paint. So let's say that you look at this function, then, so this is y equals f of x. It turns out that its inverse is symmetrical with respect to the bisector of the first quadrant. So the inverse would look like this. So this would be y is equal to f to the negative 1 of x. So geometrically speaking, the two curves are the same. I mean, or you can find an isometry of the plane that identifies them in some sense. So if for one of the two functions you have a tangent at a given point, which means that it's differentiable, then you're going to have it for the other. The only problem is that it may not the only problem that you may have is that if that tangent has to be horizontal at a given point, then at the corresponding point, the corresponding tangent, because of the symmetry, is going to be vertical, and that is going to be reflected by the rule that we're going to give. So here's the rule. It says that the derivative of the inverse function is 1 over f prime composed with the inverse function. So this is the formula. Sometimes people might call this the inverse function theorem, but one might say that this is too much of a statement. And let's see how this applies to the case. And before we see how it applies to the case of the logarithmic function and the exponential function, let's note that this derivative that you put down here should better be not a 0, because then you're going to have all kinds of trouble. So let's suppose that f of x is the exponential function, and then its inverse function is the logarithmic function. And we can ask, what is the derivative of the logarithmic function? And the answer is going to be, it's 1 over the derivative of the exponential function. And the derivative of the exponential function is itself composed with a logarithmic function, which gives you 1 over x. So the derivative of ln of x is 1 over x. And let me just note here that if we have the logarithm with some other base, then remember that the logarithm with some other base of a, some other base a of x, is ln of x over ln of a, which tells you right away that the derivative of the logarithm with base a of x is 1 over x ln a. So you have this formula, but the most important formula here for us will be this one. And this is the formula that we would like to explore. And the thing that we should say here is that there is something quite unique about this formula. I shouldn't say unique, but something that we haven't encountered yet. And let me describe right away what this is. if you look at all other differentiation formulas for specific functions that we have seen so far, you will realize that the level of complexity of the derivative is pretty much comparable to the level of complexity of the original function. So the derivative of a trigonometric function is another trigonometric function of some combination thereof. The derivative of a polynomial is a polynomial. The derivative of a root usually will involve a root. The derivative of an exponential function is the exponential times some constant number. But here you have the logarithmic function. It's a very complicated function. It's what people call a transcendental function. And its derivative is the simplest function one can ever imagine, 1 over x. And this is not just some trivial remark where we say, oh, okay, look at this thing and that's the end of the story. It's anything but the end of the story. People actually do take advantage of this. And there are places in which the logarithmic function is actually defined as the antiderivative of 1 over x. And it turns out that many properties that are hard to prove in other contexts can be proved then quite easily. So let's look at some examples using this new rule, which will be our last rule for differentiation. So let's say that we want to find the derivative of ln of x squared plus 1. Then this derivative is going to be 1 over x squared plus 1. So we think of this as y, right? So the derivative of ln of y is 1 over y times 2x. Yeah. Or let's say that we want to find the derivative of x ln x. So by the product rule, this will be 1 times ln x plus x times 1 over x. You can leave it like that. You can actually simplify it and you will get this. So in general, whenever you have a function f of x, a positive function, you compose it with a logarithm and you take the derivative of this, you find this very interesting quantity, the derivative of the function over the function itself. And sometimes this is known as the logarithmic derivative of f of x. So this is known as the logarithmic derivative. And if you have a bunch of positive functions, it turns out that the logarithmic derivative of the product of those functions is the sum of the logarithmic derivatives. And that gives us all sorts of interesting consequences that we're not going to explore. But the one thing that we would like to make sure that we understand here is how we can use this in order to find the derivative of some functions that otherwise we would have not been able to figure out. So let's say that you want to find the derivative of x to the x. X to the x is a very interesting function, right? So far, if you ask yourselves what we know that could be kind of relevant, but not the most useful thing in the world, is what the derivative of a to the x is. The derivative of a to the x is a to the x ln a. We also know that the derivative of x to the a is a times x to the a minus 1. Okay, so you have the derivative of the exponential function and you have the power rule. And you could ask if any of these two could apply to this situation, to the derivative of x to the x. And the answer is unfortunately no, because the function x to the x is neither an exponential function. In the case of exponential function, you need the constant basis, and certainly here you don't have a constant basis, and nor a power function, because in the case of power function, you need a constant exponent. So in some sense, none of these things allows us to know right away what the derivative of x to the x is. And here's where we make use of the round trip formula that we present in the very beginning. And we tell ourselves that this is the same thing as E to the ln of x to the x. And then you have this very pleasant trick where, because of the properties of the logarithm, the x comes in front. So you have e to the x ln x. And now you can apply the common chain rule. So this will be, so your y is x ln x, and then you need to take the derivative of x ln x, which, by the way, we found it right here, right? Allow me to take advantage of that and just write that this is ln of x plus 1. I mean, normally you would have needed to perform the product rule in this case, but since it's already in front of us, why not use it? Let's do one more example. So let's say that for some reason, somebody wants to find the derivative of sine x all raised to the cosine x. Okay, so let's say I want to find the derivative of this. And again, I'm thinking of this as e to the ln of sine x to the cosine x. And again, I can write this as e to the cosine x times ln of sine x. And now I can apply my usual rules. So this is e to the y, so the derivative will be e to the cosine x ln sine x times, and now I need to take the derivative of the exponent, which happens to be a product, right? So what will be the derivative of that product? It will be negative sine x, derivative of the first times the second, plus the first times the derivative of the second. Now, what's the derivative of the second? Well, I need to apply the chain rule. So I have ln of y, so the derivative is 1 over y, so 1 over sine x times the derivative of what I designated as y, which is cosine x. And that's it. Again, I repeat that this part here is nothing else but the derivative of ln of sine x according to the product rule. Okay, and with this example, we actually complete what we wanted to do. And thanks for watching.